Hello and welcome back to Machine Learning. I'm Jivita Christie, and in this video, we are going to talk about how you can evaluate the performance of classification models in machine learning. So let's begin. Now, when you're dealing with classification where there are only two classes, there can be four possibilities. So think about a cricket match and think that your model is going to predict whether the match is going to be won or it's going to be lost. So there are two things, win and loss, and there are four possibilities. So the first possibility is that the model predicted the team will win and the team won. The model predicted the team would win and the team lost. The third possibility is that the model predicted the team would lose, but the team won. And the last possibility is that the model predicted that the team would lose and the team did in fact lose. So these are the possibilities. Now in the first case, what happened is the model predicted that the team would win and the team also won. So the model was correct, and such a case is referred to as TP, also known as true positive. In the second case, the model said the team would win, but the team lost. So this kind of a case is known as a false positive case, which is also denoted by FP. And in the third case, the model predicted that the team would lose, but the team won. So in this case, this is known as a false negative, also known as FN. And in the fourth case, the model predicted that the team would lose and the team lost. So the model was correct. And this will be known as true negative because positive means winning and negative would be losing. So we always try to take positive as something that we are interested in, which is in our interest. So winning a game would be in our interest, whereas losing wouldn't be. So that's why positive is winning, negative is losing, and true and false depends on how the model actually predicts. So this is a diagram that is showing the same thing. So you can see in this diagram, this is the outcome on the vertical axis. You can see loss and win, two outcomes are there. So win is the outcome. And if the model is also saying, has also predicted the team would win, then this is a true positive. So you can see this arrow hitting the bullseye. But if the outcome is winning, but the model predicted a loss, then it's a false positive, which means it's not going to hit the bullseye. The arrow is not going to hit the bullseye. And next you have the actual outcome, which is loss, and the model did not predict loss. The model said the person would win, which you can see here. So this is a false negative, and you can see the arrow not hitting the bullseye. And the fourth case was where the model predicted loss and the team had actually lost. So it's a true negative case, and you can see the arrow hitting the bullseye. Now, based on all these things, there are some calculations that you can do to evaluate your model. The first one is accuracy. So for any classification model, the model accuracy is given by total number of correct classifications, which means true positives and true negatives. Okay, divide that by the total number of classifications done. So it would look like this: true positive plus true negative, divide that by everything, the sum of everything, which means true positive, false negative, true negative. Okay. Now, something that can help you a lot in this kind of prediction, in this kind of evaluation is a confusion matrix. So it is a matrix that contains the correct and incorrect predictions in the form of true positives, false negatives, and true negatives. And that is known as a confusion matrix. So let's go back to our example of a cricket match where we were doing a win or loss prediction. So in that case, we will be creating a 2 cross 2 confusion matrix because there are two classes, winning and losing. If you had a problem involving three classes, then you would be creating a confusion matrix of 3 cross 3 dimensions. So let's just assume that this is the data, okay? So predicted win and actual win. So this means we're talking about true positives. So there are 85 true positives. Predicted win and actual loss. Here we are talking about false positives. So this is 4 false positives. Predicted loss and actual win. This is false negative, which is 2. And this is true negative, which is 9. So we have all these values. And we can, just put those values in our accuracy formula, and we can get 94 by 100, which would be 94%. Okay. Just like you can calculate accuracy, you can calculate error rate, which is just the opposite of accuracy. So it would be basically just changing the true to false in the numerator. So we have false positive plus false negative divided by the total of everything. So if you put all these values here, you will get 6% as the error rate, which, if you notice, is exactly 1 minus accuracy. Remember, accuracy was 94%. So whatever is remaining, 6%, is the error. So if you don't want to calculate error like this and you've already found the accuracy, you can just do 1 minus accuracy. That could also give you the error rate. Now there's another measure which is known as the kappa value. So sometimes correct prediction, which is both TPs as well as TNs, may happen by mere coincidence, right? So this kind of a case can happen anytime, that your model is predicting true positives and true negatives correctly, but it's just a coincidence. It's nothing related to the model. It's not because the model is good, but just because it's just lucky that it got that correct. So these occurrences would boost the model accuracy, right? But that should not happen. That's why we have another measure which is known as the kappa value of a model, which indicates the adjusted model accuracy. Okay, so this is an adjusted model accuracy, so that if it's just a coincidence by which the model was accurate, then that can be handled. Now the kappa value can be 1 at the maximum, which represents a perfect agreement between the model's prediction and the actual value. So if the kappa value is 1, that means there is a perfect agreement. The model is completely accurate. Okay, and anything less than 1 means there is some inaccuracy, which is the case with any kind of model, right? So this is how you can calculate the kappa value. It is P of A minus P of PR divided by 1 minus P of PR. Okay, so P is obviously the probability. Now what is PA? So PA is the proportion of observed agreement between actual and predicted data in the overall data set. So observed agreement, this is nothing but your accuracy formula, if you notice. TP plus TN divided by everything. So PA is nothing but your accuracy. Then we also have P of PR. So PR is the proportion of expected agreement between actual and predicted data, both in case of class of interest as well as the other classes. So in our case, there are only two classes. The class of interest is winning, and the other class is losing, which we are not interested in. Now, finding P of PR, which means you're finding the proportion of this type of accuracy for both classes. Okay, so basically this is the formula for what you're doing. You have true positive plus false positive. Okay, and then you're also taking true positive and false negative. You're taking false negative and true negative, and false positive plus true negative. So notice here that there is a multiplication. So we have added true positive and false positive, and true positive and false negative. We have added those two and multiplied. And we've also added to this the multiplication of false negative plus true negative into false positive plus true negative. And all the denominators are simply the total number of values. So this is how you can calculate P of A and P of PR, which can be used in this formula to calculate the kappa value. So here is some calculation for the value of kappa. You can see P of A. You just have to simply put all the values from the confusion matrix. You will get 0.94, which is actually our accuracy. And the P of PR is going to be all this calculation right here. And this will lead to 0.7886. And then use the kappa formula to calculate the value of kappa, which is 0.7162, which is much less than the actual accuracy of the model that we calculated. So this is an adjusted accuracy. So this is the kappa value. Next, we have sensitivity, which is another way of evaluating a model. It measures the proportion of TP examples, which means true positive cases, which were correctly classified. And so this is a very simple one. You have true positive divide by true positive plus false negative. Why we are adding false negative? Because false negative means actually the case was true, but the model said it was false. So that's why it's true positive upon true positive plus false negative. So that is your sensitivity. Using our previous confusion matrix, we could calculate sensitivity like this. It would give us 97.7%. The next measure is specificity. So it is also another good measure to indicate a good balance of a model being excessively conservative or excessively aggressive. Okay. It measures the proportion of negative examples which have been correctly classified. And in the context of malignancy prediction of tumors, okay, so if you're trying to predict whether a tumor is malignant or benign, then specificity would give you the proportion of benign tumors which have been correctly classified. Okay, so specificity will tell you whether if a tumor is classified as benign, is it actually benign? Okay, and sensitivity will tell you if the tumor was classified as malignant, is it actually malignant? So that's the difference. And again, this is our confusion matrix. You can calculate specificity by just taking true negative, divide by true negative plus false positive, because false positive are values which are actually negative, but the model predicted them to be positive. So this comes to 69.2%. Okay, so that's what specificity is. Now let's talk about another measure, which is called precision. So it indicates the reliability of a model in predicting a class of interest. Okay. And when the model is related to this win-loss prediction of a cricket match, then precision indicates how often it predicts the win correctly. So how often does it predict the win correctly? And precision is again like this, true positive upon true positive plus false positive. So this is slightly different than what we saw in sensitivity, where instead of here false positive, we actually took false negative, right? So this formula is slightly different, and precision is 95.5% using this formula and the confusion matrix. Next, we have recall, which indicates the proportion of correct prediction of positives to the total number of positives. Okay, so a sort of a ratio or proportion to correct prediction of positives to total number of positives. So if you consider the win-loss prediction of a cricket match, then recall would resemble what proportion of total wins were correctly predicted. So this formula is also slightly different than what we saw previously. It is true positive upon true positive plus false negative. If you put all these values inside, you will be getting 97.7%. So that is the value of recall. Another way of measuring evaluating the performance of a classification model is through F measure. So it combines precision and recall. So it basically takes a harmonic mean of precision and recall, which can be calculated like this. F measure is 2 times precision into recall, divided by precision plus recall. That's how you take a harmonic mean. So using whatever we had calculated previously, precision was 0.95, recall was 0.97. Putting all those values here, F measure is going to be 96.6%. Now let's talk about something called the ROC curve. This is the last way to evaluate a classification model. So what is the ROC curve? ROC stands for receiver operating characteristic, because this was initially or originally meant for electronic devices, or rather things like telephones or something, where signal is passed and it is received somewhere. But nowadays it is used for even evaluating the performance of a classification model. So what is that? So there is a curve, ROC is a curve that helps you to visualize the performance of a classification model. It will show you the efficiency of a model in the detection of true positives while avoiding the occurrence of false positives. So just to refresh our memory, what is true positive? True positives are those cases where the model has correctly classified data instances as class of interest. So in terms of win and lose in cricket match, the model correctly predicted that the team would win. That is true positive. And in case of false positives means model has incorrectly classified the data as positive. So the team is not winning, but the model said they are winning, so that is a false positive. Okay. Now using the same example, in this case, the model, if you consider example of tumors, malignant and benign, then true positive would be where the tumor is actually malignant and the model also said it is malignant. And a false positive would be where the tumor is not malignant, but the model said it is malignant. So what is the true positive rate? It is TP upon TP plus FN. Okay, so FN is, remember FN is all positive values only, but the model said they are negative. So TP plus FN. And false positive rate is FP upon FP plus TN, right? So this is the false positive rate. This is the true positive rate. Okay. Now what happens in the ROC curve? FP rate, which is the false positive rate, is plotted on the horizontal axis. Horizontal is the x-axis, against the true positive rate, which is plotted on the vertical axis at different classification thresholds. And we assume a lower value of classification threshold, then the model classifies more items as positive. So values of both false positives and true positives will increase. And you can measure the area under the curve, which we will be seeing now, extending from 0, 0, the origin, to 1, 1, where each point on the curve gives a set of true and false positive values at a specific classification threshold. Okay, so what does this curve tell you? It gives you an indication of the predictive quality of a model. And the area under the curve, which ranges from 0 to 1, if AUC is less than 0.5, then it would say that it would specify, it would indicate that the model, the classifier has no predictive ability because the area under the curve is less than 0.5. So this is what the diagram looks like. What you see here, this whole thing is a curve. These are the true positive rate. This is the false positive rate on x-axis. Whatever you measure here, this starting from the origin up to 1, this 1, 1, 0, 0 to 1, 1, whatever area you measure under the curve, that would show you how good your model is. So if this area is higher, that means the model is better. If this is less than 0.5, that means your model has no predictive ability. Okay, So you could also consider here there are two classifiers, classifier 1, which is shown by this dotted line, and classifier 2, which is shown by this solid line. Okay. Um, so you could say that classifier 1 is better because the area under that is more than the area under classifier 2. So that's how you can use an ROC curve. So this figure shows just what we just saw, two classifiers, 1 and 2, and one is classifier 1 has more area under the curve than classifier 2. So you can say that classifier 1 is better than classifier 2. And there is a quick indicative interpretation about how much area under the curve should be there from 0.5 to 1. So if the area under the curve is between 0.5 to 0.6, you can say that your classifier has almost no predictive ability. If it is between 0.6 to 0.7, you can say it has a weak predictive ability. Between 0.7 and 0.8, it has a fair predictive ability. Between 0.8 and 0.9, it has a good predictive ability. And obviously between 9 and 1, it has an excellent predictive ability. So this is how you can interpret the ROC curve. So I'll be seeing you in the next video. Thank you for watching.